Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 22, Stoichiometry Part 3. Here are our objectives for today's video. Pause here. So whenever you hear me discuss percent composition for the rest of the chapter, you can assume, unless you're told otherwise, that we're talking about mass. And that is because oftentimes we know the masses of specific elements that we have within a compound. And then we can use that information to get the chemical formula, which we can then use to do further calculations. It can also be for mole percent as well, or the percentage of atoms, say, that are carbon within a sample, but it's just much more common to see it with mass percentage. Pause here. So before I do this question, I need to get the formula and the molar mass of carbon dioxide, which is just CO2. So to know the percentage that is carbon by mass, 12.01 of those 44.01 grams are from carbon. And then it ends up being unitless because the grams and the grams cancel out. I could do grams per mole as well as units. Either way, it'll work out. And then I could leave this either as a decimal or as a percentage. I'm going to leave it as a percentage just because I like to. And these are typically not going to be sig fig questions. So I did 4 sig figs just to be consistent here, but you could have done more or less, and that would have been fine as well. And then for the percentage that are carbon atoms, so CO2 contains 3 total atoms, 1 carbon, 2 oxygens. So it's just 1/3. You could just even leave that as is if you want. I'm going to do this as a percentage just to be consistent here. I did 4 sig figs for no particular reason. I could have done more, I could have done less. Pause here. All right, so this one is pretty similar, just that we've got a more complex molecule, and we're going to be doing this for each atom in there. So for carbon, hydrogen, and for bromine. For the percent carbon, I then take the mass just from carbon, so that is 6 times 12.01. And then I just divide it by the molar mass. It doesn't really matter exactly how many sig figs you do, but try to be consistent, not so much with your sig figs as your, like, where you round to. So all of mine for carbon, hydrogen, and bromine, I'm going to round all of them to the hundredths place with my decimal, or with my percentage rather. And the reason why I'm going to do that is because afterwards I could add them all together and make sure that they add up to 100 without really needing to worry about rounding errors and things like that. So again, it's not that you have to, it just makes checking your answers a little bit easier. So just make sure that whenever you are doing all of the things from a particular compound, if you're doing every single atom in there, they need to add up to 100%. Pause here. So empirical formula just means the simplified version of a molecular formula. A molecular formula actually describes the molecule, whereas an empirical formula just describes the ratio. Both the empirical and the molecular formula have applications. Empirical formula comes more from experiment. Molecular formula comes from multiple experiments, typically. But typically, we need to use the empirical formula to get the molecular formula, which is what we'll be doing, maybe not in this video, but actually a little bit more in class. But whether you are working with the empirical formulas, let's say, for example, CH of benzene, or the molecular formula C6H6, if I were to perform the calculation for a percentage by mass, it would be the same whether I'm using the empirical or the molecular formula. Pause here. So sometimes experimentally, you will be able to get the percent composition of a compound, and then you're going to need to use that to get the empirical formula. We'll add on later how we get to molecular formula from there. There's just another pretty straightforward step. So I'm going to give you these 3 steps. There's definitely other ways to do it. I just consistently find that this is the easiest way, so that's the way I recommend students do that. So if you have the percent composition, just assume that you have 100 grams of the substance. It's just the easiest number to work with. You could have picked a different number and it would have been fine. Then we're going to calculate the number of moles, and then we're going to find the smallest whole number ratio. Let's take a look at an example to show what this would actually looks like. Pause here. All right, so I'm just going to assume that I have 100 grams, which means that I've got 82.2 grams of nitrogen and 17.8 grams of hydrogen. So then I just convert both of these to moles. And then I need to find the smallest whole number ratio. The easiest way typically to do that is just to take your smaller number or your bigger number and put it over top of your smaller number. From here, I get 2.99, but that is approximately equal to 3. So what that means is I've got 3 hydrogens for every 1 nitrogen. So my formula is NH3. If you did H3N instead, that would be fine too. NH3 is how it's supposed to be written, but there's nothing in the problem that indicates that. So it would be okay if you had written it that way. That is all for today's video. Thank you so much for watching and have a great night.